radar signal or radar emission, it has been divided to sub-pulses. So each pulse represents a bit. So for this one, it became like a radar and communication. If you have a receiver communication available at radar side or radcom, it will receive and decode the informations easily. Others, they use that waveform designed to probe the target and in the same time to convey informations. So other people, they use index modulations like code shift keying, in which each waveform is considered as a code, represents a bit, so it can be transmitted normally with radar emissions. The others also, they use frequency hooping, means that they enable the frequency hooping to be transmitted with the MIMO to carry informations. Other, they use FSK, and this was our contributions, which we use two orthogonal frequencies in which each frequency represents a bit of information. So we will see it later on. The other, they use waveform permutations, means using different antenna waveform pairing to carry communication signals. So the contribution, basically, it came from the idea that, okay, there is now a new field which is called radcom, but this radcom still is insecure, still needs a lot of investigation. So what we have done in this paper, we have secured our system by protecting our communication data is going to be transmitted with radar. So in this scenario, if we have a beam pattern signal are transmitted, so the red signal is going to hit the target in main loop, it will hit the target and it will come back. But we don't want to send only 2 bits, we want to send m bits. For that, we use q is equal log to m bits, which it can be transferred, traveled with the radar echo. So we check the conditionality, the orthogonality condition for that, and we give a threshold for each bit is going to be transmitted, so that if the threshold value of this bit received at the receiver is less than a specific threshold designed, so it is equal to 0. If it is greater than that threshold value, so it is 1. Now, let's have a look about the array factor of the radar. So if we assume that we have a uniform linear array of ULA system with n independents, and we see that from equation 6, the array factor of this radar system, it can be like that, where as shown in equation number 6, so that the gamma here is equal to pi by lambda d cos theta, and theta here is the angle of arrival, and z here corresponds to the positions of zeros in the array factor along the fixed angles. So V0 at Z1, Z2, Z3 as shown in equation number 8, when after we give it a coefficient weight vectors in equation number 7, then we transform this to factorized form as shown in equation number 8. So our array factor in factorized form can be now transmitted. So how we embed the communication? Just we have, if you see from the figure down here, this is the communication which we have designed it before. So just we injected to the radar arrays, and we give here, we suppose that we have 4 stages of nulls. Stage 1 represents null number 1, stage 2 represents null number 2, stage 3 and stage number 4, which is going to be protecting the informations at each of these nulls, as we will see it in the simulation. So the output of the array factor at stage number 1, x11 as shown here, x12, the output array factor of it's like that, the output of the array factor at x13 also and x14. By this one, we have the array factor at stage number 1, and we have a communication which we have designed it before. Now, the multiplications of these two communications or injection of the communications to the radar signal, it can be shown in equation number 8. By this one, we have a radar at the first stage number 1 with protected. So same thing at stage number 2, we will have the same thing, x2, which represents z minus z1 into z minus z2 and so on. So the baseband signal are going to be transmitted here, as shown in equation number 10, and also for the other one at stage number 3, the equations can be shown at number 11, and the final stage it's at equation number 12. So, now this was the transmitter side. What about the receiver side? This was our designing at the transmitter. At receiver side, we designed a receiver, a communication receiver, a simple communication receiver that can receive the transmitted communications which has been transmitted in side loop levels with the array factor power of side loop levels, which it can be received with the propagation factor beta and the angle of arrival from the ELF communication receiver. So after passing it to match filter, we will just remain with the beta, which is a constant value, array factor, which is only just designed carefully by the designers for the power of side loops, and the bits, which will pass through the threshold. So, is radar is going to get benefits from this as we are talking about DFRC systems? Yes, it will get a benefit that yes, radar is going in main loop, but when we inject also F1 and F2 to the emission of that radar, means that we are going to calculate the Doppler and as well as the range. So here, if we can see that the R is the target of the range as in equation number 15, and we can see that frequency 1, frequency 2 are shifted in their Doppler as shown in equation 16 and 17. So the Doppler frequency components of the two received signals can be calculated as shown in equations 18 and 19. And these modifications, it's not yet in the thesis because we have modified based on the reviewers who asked for that after acceptance. So we calculate in the range. We take the phase difference between the two above components of F1 and F2. Then from this equation we can easily get the range based on our different phase difference of the frequencies. And it's clear that from the above equation the phase difference can be used to measure the range of the targets. So for radar and ambiguous, then just we keep delta phi is equal to phi, so that we can the system the maximum and ambiguous range. So moreover, if the difference between the two frequencies is large, this will lead to range accuracy due to the proportionality change in delta F. Now we come to the simulation part. Simulation part, here if we can see from, for example, our null, it was available at 35. But the JML is trying to attack a communication at angle of 40. Then easily just we manipulate our system so that the null here of power, it can come to the angle of 40. By this way, we give the JML a null. So he cannot get our communication. Imagine that the JML is trying to attack the edge of the radar emission, which also carrying F1 and F2. Our system here, yes, we focused on side loop. We focused on transmitting a communication in side loop, and we did not assume that there is a communication receiver available in main loop. But we also tried to get a benefit of this by protecting the communication and the radar available. If the JML is trying to attack at angle of 75, we just move our null to angle 75, and same thing, we can move our null from angle 120 to 125 to protect our communications available inside loop region. At the same time, if the JML is trying to attack our communications, which it was available at 40, so just we move the null from 160 to 140. But in case of multiple JMLs are going on, in this case, we have to make one reference beam pattern, and the other beams, we give multiple beams that can dynamically move and protect our communication based on the movement of the JML. So here, if we can see that the radar performance did not affect as before. Regarding also the literatures, when we compare our work with the literatures in terms of RMSC and SNR, also the thing which we have found that the probability of resolution under both working conditions of DFRC under shifting our communications from JML or protecting our communications from JML or keeping it as it is it shows that improvement in protecting our communication signals, and also it shows that the probability of resolutions under both working conditions and proposed DFRC systems. We found that the proposed independent null steering, dual function radar communications and the gamer avoidance outperforms the other DFRCs. So, the probability of resolution now, when we compare it to the other existing techniques available of DFRC, it's also slightly perform better. The bit error rate and this SNR here, it has been improved when we compare our results with the existing ones available in the literature. That was one story. The other story, which is the milestone, started is here from throughput enhancement or from using a rest mode of communications or radar as a communication. You can imagine that 1 microsecond is going to be transmitted for 1 microsecond for pulse width, and 1400 milliseconds are just the radar is waiting, listening. Why we did not use this much time to be used for a communication as well? Besides that, why we did not use a main, as the previous people they have done, just they used a pulse radar to transmit a communication in side loop or in both, I mean in active mode of radar, while they never thought about the rest mode. Here was our things. So, if we transmit a communication, let me just give you a brief, quick brief about the rest mode and active mode. This is the red line here, rectangular, represents the time energy taken for the radar to be transmitted, which is pulse width of the signal. And after that, the radar goes for silent mode during all the PRI pulse repetition interval time. So the time, total time is TW plus tau R. Tau R here represents the rest mode. So, before we start also to this, we thought about two things. How to calculate the pulse width and how to calculate the time, time rest mode based on our timing signals, and what about the time rest mode based on the distance of the time. So for this we designed two generalized side loop cancellers. Here, just I give you the brief from the literatures. Look, if you can see pulse width here for radars, any type of like those radars of short range radars is 1 microsecond. Whereas the others has 1425 microseconds. Look how much huge time we can use it for a communication as well. Or even if we go for frequency looping radars, 1 microsecond is the pulse width, while the pulse repetition interval it is 333. So, let's come to the contribution. In active mode, we design generalized side. We bring generalized side loop cancellor, and we design it so that it can work as a radar in main loop and communication inside loop. So, the input signals, the desired signals will pass in the lower branch of this, which is through the cosine weight vector, which will give me the desired signal which I want. And also I have to manipulate my signals by using adjustable weight vectors as shown in GSC. So the result of this was radar in main loop, communications inside loop by manipulating also the weight, the gain vector. The gain vector here, it's the constraint values which we have it, which consists of the constraint matrix here. Like I have produced like one radar is available at the main loop as theta t here, it can be shown, and the other A theta t, the steering vectors, the other steering vectors here represents the communications available. And we have generated 4 communication transmitters beside the radar. So then we go through the mathematics of that, and the result was that radar available in main loop and 4 communications are available inside loop region. This was our achievement up to now. What we have done, what they have done. But the thing is that when we use the rest mode, this is the thing. The rest mode the same GSC is going on in rest mode. And we also manipulate another, we bring also another rest mode, another GSC I mean. So the Q max, the throughput of communication link during one pulse repetition interval, it's equal 1 plus tau r by t. Now, we made also another things, we calculate all the throughput of all the existing papers has been done before, and we check their throughput if they apply a rest mode. So, many factors, we have studied many variables in that. So, here look, during one pulse repetition interval, means that you have active mode, which is going in the red line as shown. Red line, the red one is representing the higher one, representing the radar signal going. The other 4 red lines are representing communications only in active mode. But in rest mode, as there is no radar, so the dashed line is going to be none. But the other communications, which it was already produced in main loop, in active mode, inside loop of active mode, it has been continued as shown here. So, the thing is that until now we produced a buffer for radar to be transmitted. But how to again embed a communication to that? By embedding a communications, only just we change or manipulate with the variables of the side loop region by using optimization, problem of optimizations. And here we can see that we produced like 2 levels, the high level representing the 1 bit, the lower level represents the 0 bit. So by this way, we transmit a communications with 1 and 0. Besides that, if you see both lines during active mode, both lines, they have identical value available in the main loop for radar. Now, but if our target is not far, if our target is near, why we spend a lot of energy to that target? By this one, we manipulate also, we design our system carefully to transmit energy to a specific target available in the to the specific communications available in a specific distance. So our system became more intelligent by transmitting a communication. For example, at the first one, if we can see here at -5 decibel, if the communication receiver is there. Other one, if the communication is available, I'm talking about red line only, if it's available at -10 decibel. The other one, if it is -7 decibels, and so on. By this one, we generate 8 side loop levels. 4 for the red line, for the ones, and the other 4 lower, which it is a dashed line here, represents the 0 informations are transmitted. So, that was in active mode. In rest mode, we have also the same thing. We can see the same data which we have produced in active mode. It has been also occurred inside loops, where if you can see from this figure, the radar signal is absent. Only the remaining is the wireless communication available towards receivers. Again, also with the same distance of the target and the same manipulating the powers toward the communication receivers. Outcome means that we are going to check every system we have and what is the spectrum available and what is unused spectrum, and just inject. If it is radar, inject communication. If it is communication, inject whatever you want from the RF surfaces. But one thing which I have seen, and I hope that one day we have a test laboratory in this university, so that we can do Internet of Things, we can do Internet of Radars, means that just we inject radar to the Internet of Things or wireless communications. And we have also to think about artificial intelligence and machine learning for RADCOM. We have to focus on RADCOM for the 6th generation. It will be definitely 6th generation. Radar will be now, we will see from now onward, we will see the 5th generation of radar, 6th generation, because it will just be, it will grow up with the communication generations. The mitigation and regarding your other questions, here also we have our data rate here. It has been, if you can see that, our paper, which we use a generalized side loop cancellers, or which we use the rest mode for that, it can generate paper has been published, and it can be if the data rate it is like 100 kilobytes, or it's in the tens of megabytes. Our paper can produce it to tens and tens of that, because you know in active mode only just they are transmitting like for 1 microsecond. The communication is going inside loop, it's in for 1 microsecond, while the rest mode here it's like 1423 microseconds extra to 1 microseconds, and you can imagine the data rate how it will be here increased. This is regarding your first question. The second question, which you are talking about the mitigation of interference, means that I want to tell you one thing. This technology has taken 3 directions. One direction was the coexistence directions, which leads, which manipulate and trying to reduce the interference mitigations between 2 separate conventional radar and conventional communications who are trying to approach one joint system. So the systems comes to the signal received at the receiver, which receive from 2 different transmitters, deals with it as if I want to calculate the radar signal, then just I will consider the other signals as the interference and noise to the radar. By that, I will use also match filtering, as I have done it in one paper, and I have to just extract my signal, the desired signal. If it is in radar, I will consider the radar signal, the noise, and the other also signals coming from the other interference to be as interference. All these I will just remove them by using waveform, which I transmitted waveform signals, and just match filter our signals. Similarly, for the communication, if I want to receive a communication signal comes from different radars and communications, then just I will consider the others as interference. But the main important point was also the co-design systems, with means that one signal goes as communication and radar in the same time, and when it is one signal from the same system, means there is no interference within that system. Clear, sir? Thank you so much.
Okay, and one more question.
Yes, yes, sir.
You use adaptive beamforming, like this, because you're using beamforming to steer the lamp.
Yes, sir. Yes, sir. We use the... Yes, sir. When we use the adaptive beamforming, definitely it improves our data protection, and also we use the adaptive beamforming also to embed communications in a weight vectors.
So currently, have you used that?
We